All right. So this is going to be our introduction to data structures and algorithms. In the curriculum, it's up here, and this is important. It's under 11. And the reason is on this module, we don't do it like one every day, one after the next. We've decided like we do one every Friday and we start mixing it up a bit more. And you can kind of see on the Google Calendar what is happening when. But both here and in terms of like a YouTube playlist, because I'm going to make a playlist, I think just for algos. Um, and in terms of demos and notes, it's all going to be in this one directory, just so everyone is tracking on that one. So today we're going to really get introduced to these concepts. We're going to talk about why do they matter. We're going to use a very simple search as sort of an example to discuss. And what we're going to discuss is the idea of runtime complexity or time complexity, what's also called big O, which is often written like this. And we call this big O of n. And so, and we'll talk about what this means in a minute, but I just want to kind of introduce concepts. We would call this big O of n squared. Or for example, this would be big O of 3, which is, we'll talk about what constant time is, but constant time. Has anyone run into these concepts before? Whether it's a little or a lot, time complexity and big O?
Yeah, it's kind of review a little bit.
Okay, awesome. Did you prior to Code Platoon or was it in Foundations of
It,
Programming or
it was in Foundations, but I did have exposure to it prior too.
okay, perfect, awesome. Yeah. So and like in a nutshell, like how would you describe maybe like the idea of runtime complexity or what Big O is?
Essentially just how efficient your algorithms are in terms of running.
Yeah, exactly. How efficient is our algorithm in terms of running? And the two classic kinds of algorithms for learning um, and talking about this stuff are search algorithms to find something in a list or a nested list or any other data structure, and sort algorithms, right? If I have a list of random numbers, sorting them in order. Um, And today we're going to see a search algorithm called binary search that's really cool that will introduce a really valuable concept of the logarithm and is of a particular kind of search algorithm called divide and conquer. And we'll talk about that, which will be really cool. But we'll be building on this through each of these lectures. Um, any questions about the agenda before we dive in? And what I'll probably do is I'll probably just kind of have the lesson up on the side. I think that can be useful for people to see, especially as I'm navigating sometimes through the VS Code. And so we're gonna talk about linear search. We're gonna do a little refactoring of code, talk about complexity or efficiency. We're gonna learn about complexity analysis and build a little binary search. And we're gonna start off over here. So, you know, there's a lot of stuff here. And in fact, we'll just have our tail draw ready to go. Let's just talk about this real quick. Why does this matter? Why do we have to learn it? Because while the AI stuff was maybe feels way further away than kind of OOP and stuff, this stuff is going to be a bit more abstract as well. This stuff is sort of like the classic computer science curriculum that CS undergrads learned. Um, like I think my very first introductory programming course was sort of like intro to programming and object-oriented programming. And right after that was data structures and algorithms. And and there's a whole stuff that builds on that. And kind of like with OOP, this is just really the highlights of what's really a semester-long introductory course. Um, so why are we learning this material? On a very practical level, because you'll be asked about it in technical interviews. Um, they're called whiteboarding interviews where you might have to just write an algorithm on a whiteboard and then talk about how efficient it is. That approach used to be extremely popular. It is still the standard at places like Google and Facebook and Microsoft and stuff like that. Because those big West Coast tech companies, they kind of design their interview process to privilege people who just came out of a 4-year CS undergrad because they've been grinding algorithms all day. But there are good reasons. Most interviews don't have as much of this. You're only going to see it a little, not a lot, but there's good reasons why it's there. Um, because it touches more on math, it is used as a way to like assess a candidate's skill set at certain things. But also, these are the fundamental concepts behind how programs and computers work. I've never written a search algorithm like and been paid money for it in my life. Most software engineers don't have to as part of their job. Um, However, I'm really glad that I learned about all this stuff. And the analogy I like is your physician, for your yearly checkup might not, be able to do like DNA recombination and be an expert, but would you want them to not know anything about DNA at all, right? Like my doctor isn't going to be doing anything with my DNA, but I sure want them to know what the heck DNA is. And I wouldn't want to go to a doctor who didn't. And I think that highlights some of the importance of this. But there are other reasons why this is important too. Um, there are roles where this stuff starts to matter. Doing software engineering at scale, where you have to think about, so think, say, millions of daily users, like Amazon, Netflix, Google, Airbnb, Reddit, the list goes on, where how fast does my code run? Because time is literally money, because cloud compute charges a fraction of a cent per second. Plus, the longer something takes, the more servers we need. How much memory, hard drive space does my code take up? And think Netflix and scrubbing through video files that are stored in the cloud. A video file is big, it's terabytes, right? How does that happen? Does the whole video file live on one physical server? Does it get broken up into chunks? Does it get put in different places? Do I have to load the whole thing into my computer's memory? So there are real concerns here. And then the big one here, again, to use the engine analogy that we used with AI, is, you know, the way to have a long career is to understand the fundamental thing. And our job is to know how computers work and be able to help other people solve problems with them. Right. And so the more you learn about this, the more career options, the more career security, the more career longevity you have. And this computer science stuff is about how computers work under the hood. And the AI stuff is as well. Um, like for example, like I've never created my own database from scratch in my life. Very few people do. I still had a semester long course on relational databases. We're still going to learn about it later. And we use databases as one tool in our toolbox when we're making programs. You know, our web app will talk to a Postgres database. And that's what's going to happen with this AI stuff as well. We're not going to train the models, but our web app is going to talk to some model that says, you know, if the user uploaded inappropriate content or something like that, right? A binary classification model for, well, I guess that would be multi-classification. Um, Point being, these are going to be tools that we're going to use, and our job is really to understand how these things work, which is a journey. And so the goal here today is to really give you all, I think of it as the keys to the kingdom, because technologies change, tools change, concepts remain. All the AI stuff we've been learning about, all those concepts were figured out probably, I don't know, 1960s, 1970s. And all this stuff, again, you know, figured out around then, if not earlier. So the more you learn these concepts, as the tech industry changes and there's some new programming language and some new framework, learning this stuff will make it easier for you to learn that stuff, which is really good for your career. So that's sort of like the big picture of why this stuff matters. Do folks have any questions before we dive in and actually start talking about code and concepts and all that good stuff? Okay, cool. Let me go ahead and make a file here. Um, Call it timecomplexity.py. And let's write a little code. Mm, I've got a list of numbers here. It is has a length of 15. It's got 15 elements in it. And I'm getting a notice here. My internet connection may be a little spotty. So if folks start to have issues, let me know. Let me see. I'm not sure if there's anything I can close out. Yeah, I think we're okay. Um, let's say I just want to print out each thing in this list, each element or item in the list. How many steps or operations did my program just perform here? Not a trick question.
I mean, it performed one thing 15 times.
Yeah, exactly. It did one thing 15 times. And if we can, I'm not an expert with the debugger. Um, there we go. Let's add run and debug, Python debugger, debug the current Python file. Beautiful. Let's see, is it looking for a breakpoint? It is. So I'm using the debugger, which lets me control the exact behavior of every single step in my program and freeze it at a moment in time and look at the value of every single variable. And, Jack, just like you were saying, we're about to do one thing 15 times. And here we see the variables I've created and their values. And inside that for loop in the scope, there is this variable L, and it's got a value of 1 right now. And if I hit this next program, the code will keep executing until it gets to the next breakpoint. And since the breakpoint is right here inside my loop, when I hit this play button, the flow of execution of my program is going to be, it's going to print this, it's going to hop up here, and let's put another breakpoint there, and we can watch it go step by step. And there's no special variables that we need to worry about, or global variables. It's because it's just the one. Um, and now it prints out the second thing. And it's a little hard to see because the terminal has put all this extra kind of cruft in there. And let me give us a little more screen real estate, in fact. But if you all look all the way down here, we can see that our program has done three things, right? It's printed out something three times. Oh, in fact, I think it's done it twice. I'm not sure where the 15 came from. So please disregard the 15. I think that's,
It came from the length of my list.
oh, that's what that is. Thank you so much. Yeah. So disregard 15. That's length. I should have added a message in the print statement to make it clear. Our program has done one thing twice. We've done two operations, right? This for loop, we're not really counting that. Yes, under the hood, Python is doing something. But if I think about sort of if I was running this program with an imaginary machine and I was not a physical actual computer, this is really the operation. And this is what we're counting when we talk about operations and when we talk about steps and how many steps does a program have. And even if I added something here where I just said print on to the next one, and we get our third thing, and it's not even going to get there because the debugger isn't aware that this line of code exists. So I'll add that one in a minute. On to the fourth thing. And someone was saying the other day how useful the debugger is, and it is because this is how you can really see exactly what the computer does when it runs your program. And that's the mental model we really need to build up. Because once you build that up, it's way easier to debug and you can do things more effectively. And we're going to go ahead and print this out 15 times. Um, and we can change this. Maybe let's grab an index and we want to do something like a range. I think it might look like this. If I have my range wrong, please let me know.
When
Oh, in um up here? Oh, here, you
yeah,
mean.
yes.
Yeah, thank you. And this needs to be changed to my list times. And let's, instead of printing the index, let's print out like the step. And just for fun, let's add a print statement there so we can watch both happen. And let me just clear the terminal. And now we can run through this. So my for loop is doing two things, but for each thing in this list, it only does those once, right? So like, yes, I'm doing two things here, but how many times do I do those two things? I do it 15 times, right? There's still 15 steps. Step 6, step 7, step 9, step 13, step 14, step 15. I can add all the print statements I want, and I'll still have 15 steps unless I add more things to the list. And in fact, instead of, printing this out, let's print out, what was it, 15? So let's do something 1500. And I'm not going to use the debugger for that because that would be a lot of steps. But we're just going to run it. And we've got 0 through 1499. So the thing about programs and real world software development and stuff is that things get big, right? Text files are big, video files are big. So what we really care about the efficiency of our program, it's not about how many print statements I have in here, right? What I care about, what matters is how many times do I go through the loop? How many operations, steps? And for this is fixed because I hard coded this. But for this right here, and this is not a trick question, what factor determines how many times we go through the loop? Not a trick question.
The length of your list.
Yeah, it's the length of the list. And the length of the list we're going to always refer to as that's really, we can think of that as our input size. We'll always see something like input n, right? And so time complexity cares about when n gets big, when the input size gets big, because it's when n gets big that our program takes longer to run or takes up more memory, etc. So analyzing algorithms, figuring out the efficiency of our code is about figuring out how many steps it takes to do something or how much space. A step is really time, right? It takes, I don't know, a nanosecond, a millisecond for Python to print that print statement. Maybe if I was on a Windows machine or newer Mac, it would take a fraction of a nanosecond less. We don't care about any of that. When we're analyzing these algorithms, we're imagining this sort of imaginary computer where everything takes the same amount of microseconds because I'm not interested in like those real world, like engineering nitty gritty things. I'm interested in the performance of my algorithm, of my code, right? So how many steps, how much time, or how much space it takes up to do something. So that's what's called analysis of algorithms. That's what all this time complexity um, and big O and everything is about. And because of that, the things we care about um, are when things get big. That's what we really care about is when things get big. And just to do a little bit of drawing here, and actually I'm going to use one of my favorite, the AI tool Find that I'm really liking. Show me a really nice graph representing big O time complexity for n squared exponential, etc. And it's going to come up with something really nice, and it's going to give us a lot of nice links along the way. And we do have a nice diagram in the curriculum as well. But I feel like Find has really been killing it recently with this. So let's see what it comes up with. And we'll give it just a second as it does that. And there we go. And let's see if I can make this bigger. Um, there we go. And let's take a look at this graph and talk about what we see here, because there's a couple interesting things. We've got our input size, right? Like the list that we just had. How many steps does it take me to print a list? Or more importantly, if I need to find something in a list, the simplest way is to start at the beginning and go through it one at a time, right? That's probably the simplest search in the world. So, what matters when we're searching through for something in a list is not the easy wins. Like if I've got a list of 1, 3, -8, 22, 19, 4, -5, 0, and let's see, that's 1, 2, 3, 4, 5, 6, that's 8 things. I'm definitely doing powers of 2 here, right? N equals 8 or 2 to the third power. Because computers are binary, everything is powers of 2. So we're going to be seeing lots of powers of 2. And let me make myself a nice little pointer here to work with. And I'm using an example of 8, but instead of 8, think 16,000 or 10,000, right? Think all of the people in the United States that the IRS has in their database, or all of the users on Netflix. And let's say our target is 1. Well, this obviously is easy. It takes me 1 operation to get there. If our target is, 22, well, that takes me 1, 2, 3, 4 operations to get there, right? Because I have to probably do something like this. And let me change the color here. Search, we'll just call this list LST. And we'll just do, for L in LST. And we need a target. If L equals target, we return L. And maybe if we never find it, we return none. Right? So we've got our loop. The number of times we loop through is going to be the length of the list. We don't, even if this was 500 lines, that's not what we care about. We think of everything in here as one operation because it's the size of the list that makes our program's complexity, its runtime complexity grow, right? And with 22, we're looking at 4 comparisons. Now, if the target is 0, we're looking at 8 comparisons. So if I have 10,000 people in the list and, let's do even better. Let's say I have 1 billion people in the list. We're in China and we've got some massive tax database for like half the country or something. And my boss, our boss, has asked us to write an algorithm to find someone in that list by their name. And for whatever reason, this is the way we have to do it. If I need to tell my boss, how many compute hours I need on AWS or how long I need to run the server or whatever for to do this, do I care about if the name I want is the first or the second or the third or the fourth user? What's the information that's really useful to me and my boss in that scenario? And this is a little bit of a rhetorical / trick question. Um, and the answer is we care about the worst case scenario, right? And what's the worst case scenario?
It's not found.
Um, that's a good point. How many items, let's say our target was 100. How many items in this list of 8 would we have to check to see if it's in there or not? Not a
8.
trick question.
It'd
We
be
got to
8.
check all 8 with our simple search, right? Because we're stuck with simple search. I have to go, is this 100? Is this 100? So on and so forth. So it absolutely sucks if we don't find what we're looking for, but it takes just as long to discover something's not in there as it does to find the last thing, right? So what's the worst case scenario for how many steps it takes us to find someone in this list or figure out they're not on the list?
Over 1 million.
You have to go through every iteration of it.
Yeah, exactly. We have to go through the whole thing. So our worst case scenario is going to be n, number of items, length of list, set, right? The worst case scenario is going to be, if we're using simple search, the number of things in the list, right? Because I do one operation and I have to go through for each thing and I have to go through each thing in the list. So this is what we call big O. And we could say big O of n, where n is really our input size. Right? And let me drag big O over here so we can see it a bit better. And we might as well put a box around big O just so it's visually distinctive. So when we're talking about simple search, we would say simple search has big O of n. Um, Meaning that however long the list is, the worst case scenario is we have to search through the length of the list. We have to do those n operations. Does that make sense? I just want to check in because I feel like I got a little twisted there.
So it's like so in the big O notation, O and then comma or parenthesis n is like the absolute simplest maximum amount of steps it'll take to solve whatever you're working on.
It's the worst case scenario number of steps. Does that make sense? And I think you were just saying that in slightly different words as well. So I think you were on the money there. And again, the reason we care about that is because we're engineers, our job is to estimate, and because if we've got, a giant tax database in China with 1 billion people, we're going to be searching this thing all the time. And at some point, we're going to hit our worst case performance. And that's when the overall performance gets really bad. So if I think about every algorithm in terms of worst case performance, I kind of have a common basis of understanding. And then I know that in every other scenario, the algorithm will return better, will perform better, right? Plus, I don't know what my target's going to be. So we have to think in terms of worst case. Though as you get more complex with that stuff, you do get into thinking about the shape of data and stuff, but that's kind of outside scope for today. So, we can talk about Big O, and there's a couple different kinds of Big O. And let me give myself a little room up here. There's Big O of n. There's even Big O of 1, what's called constant time. And simple search is not a constant time algorithm. Simple search is a linear time algorithm, right? A constant time algorithm, and let me drag these guys over here so they kind of stay where they belong. I think you all will be pleased to see what a constant time algorithm looks like. This is the classic example of a constant time algorithm. Let me just get rid of that equal sign. I'm not sure why that's stuck in. And now if I run this guy, oh, I do have those. Let's just get rid of that. How many steps did it take to grab our name? Well, there is something going on under the hood here with Python, undoubtedly, as you all probably intuited. And when we talk a little bit about how computer memory works later, we can get into it. But really, in essence, somewhere in memory, Python has kept track of which name is where. And so when I say, get me Alice, Python says, no sweat. Alice is in memory location 5. Here's Alice. So this is a constant time operation. It doesn't matter how many users I have in the dictionary. It's always going to take the exact same amount of steps, right? There's not like the amount of operations it takes me to find someone in a dictionary does not increase as the number of things in the dictionary increase. And so that's constant time.
Is that
Um,
because it's referencing the memory location?
um, yeah, in essence, yes. Like with the list, the way to think about it is like a list in memory. Memory is kind of divided up into chunks that are all the same size. Like if you go to like some sort of, you know, deep suburbs housing project where each lot is the exact same. And so here, you know, maybe we have like the number 4, and here maybe we have the number 2, and here maybe we have the number 3, and here, you know, whatever. And then the computer has, just like houses on a block have addresses, and each address is more or less sequential. You know, maybe this is X123, and this is X124, and this is X125, and that's X126. And if I make this longer, so this part of the zoom always gets me. There we go. And we'll just add a new one here. And this is X127. So, and this is essentially how things in a list are stored in memory. A bit more technically, this is really an array data structure. Lists actually give us more. But so just like we had to search one at a time through here, the computer has to go through this array or this list in memory to look for the thing. And so under the hood, a list in Python is stored like this. A dictionary is stored a bit differently. There's still some of this going on, but what Python does when it makes the dictionary is it kind of front loads everything, and makes it easier to find stuff. And I don't want to quite get into that right now, but you can think of it as maybe, and this is not a bad representation of the computer, like maybe we have just a little bit of room. You know, computers can store stuff in this array or this list format all day long because everything in memory is organized into blocks. And if I have the first address, I just need to add 1 to it to get the next one. So if I know everything is in order, it's easy. So the way that sort of the actual hardware of memory and hard drive space works means that we can do this all day long. The computer also has other ways of storing memory that are more expensive and take up more, like, are just more expensive to do. I think they're like called registers, or cache is actually, I think, the really good term here, where maybe there's a couple things that we can have on hand. You know what I mean? And so maybe Alice is there, and maybe Bob is there, and Carol and David and so on. And we've got Carol and David. And this is a little hand wavy because I do love this topic, but I don't want to get too lost in the sauce. But point being, that when Python creates a dictionary in memory, it's kind of taking an advantage of this like faster way of looking stuff up without having to search through a whole ton of things. So in effect, for our purposes, because remember, we're not thinking about how many milliseconds Python takes on my, M1 Mac Air from 2020. We're thinking about the algorithm in the abstract. So we do, in fact, deliberately kind of ignore some real world stuff so we can have a more theoretical analysis of the algorithm. So the dictionary we can say is constant time. It's going to take exactly one operation to look up anything in the dictionary. Does that help answer your question and sort of make sense?
Yes.
Yeah, and I realize I went deep on that because I do love talking about this stuff. So I just want to check in with folks to see how people are feeling. Because I know I've been jumping around a bit. Are we tracking? Are we a little lost in the sauce? How are we doing? Awesome. So, dictionaries are great. And this is why, like, one of the classic leak code problems is how do you look up, write an algorithm to look up a list of users in constant time. And often what we might do is build a dictionary from a list, or, I create a user address book and we're going to use a dictionary and we get to then get a constant time lookup. And that's good for certain things, right? But it might not be good for other things. And so this is one of the really fundamental kind of distinctions is algorithms that are constant time, ones that are linear time, and thinking about when is the right, which one of these is the right tool for the job at hand. Because they're all just tools in the toolbox. There's nothing wrong with linear time. Most stuff is not constant time. And the trade-off here is really space. Without getting into it, dictionaries take up more memory space. And pretty much everything in computing is like trading time for space,
But
or space for time.
over time, I thought what we were taught is like space, space is cheaper, than it used to be.
Yes.
So we're not concerned with that anymore as we
Yes.
might have in the past.
Yes. Exactly. That is very, very true. And when we talk about analysis of algorithms, you can analyze it both for how much space it takes up. For instance, our list over here, we would say it takes up a space of 8 of n, where we just imagine like 1 unit of memory for each element in the list. If we had to create other lists along the way, then maybe that adds a bit, but really, when you hear people talk about algorithmic complexity, unless they say space complexity, we're talking time complexity. Um, Space, a couple decades ago, it was totally different. And, you know, even as like junior engineers, we had to really make our algorithms and our programs space efficient because a megabyte was a lot. When I was a kid, like 500 megabytes was a lot. I've got what, like 50 terabytes? Something like, I don't know, 10,000, probably more than 10,000 times as much space, right? If we were Nintendo coming out with the very first Nintendo game, you know, think about how much space like an image asset might take up. Like we probably couldn't fit an image file in an old school Nintendo at all. But these days it's a non-issue. That said, if we're working at Netflix where we have big old high definition files for movies, then space does become a concern again. But yeah,
So I have a quick
yes.
question. Sorry to
No, no,
interrupt.
no, please.
So basically, like the larger the input size, you want to try and use a constant time algorithm versus a linear.
The bigger the input, the more efficient you want your algorithm to be. The reality is, outside of a dictionary, there's not a lot of constant time stuff, especially for sorting and sorting. Um, Even linear, like for searching, linear is easy to get. but for sorting, it's very hard to get a linear algorithm that would sort this. So you can't always get what you want, so to speak, to quote the song. But you're absolutely right. Like we want our algorithm to be more efficient. And in technical interviews, if you're doing a live one with someone and they give you a problem, a good thing to always ask is, do you want me to think about really big input sizes or not? And they'll probably say, don't worry about it now. Let's get the algorithm working and then we can talk about it. Because, you all have seen everyone has seen a leak code problem. Is that correct? Down at the bottom of the problem description, it always says like n is less than or equal to 0 or greater than or equal to 0, but going to be, less than or equal to 1,000, right? Um, and we don't really have to think about it, but if someone said, okay, I need you to write an algorithm to sort a billion names, then we absolutely need to think about efficiency. If I know that like I'm working at Code Platoon and we're never going to have thousands of users, I don't need to worry about efficiency to search through a list of names, right? It just doesn't matter. Because as to your point, Jason, computers are way faster today than they were before. A couple decades ago, maybe it would have mattered a bit more. But the principles remain, and they are important to think about because, think about working at a healthcare company. Think about working at Walmart and their database of products and just the list of how much stuff is in there, right? So you run into these things still in the real world where you have to think about input size and how big is the data, even though computers are fast. Does that make sense? Yeah, great discussion and great questions. And I think I'll screenshot this real quick. And I'm then going to clear it because where this is going, and we will eventually build a binary search algorithm, but really the goal of today is getting familiar with big O and time complexity. We do have assignments for this though, so you will be able to get a bit hands-on. If we go back to this chart from way before, now I think we're in a much better position to understand it because we have a strong understanding of what an operation is and of what input size is. And by the way, look at the scale on this graph. This is not 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is 10 to the 0, 10 to the first, 10 squared, 10 cubed. What is 10 raised to the 0th power, by the way?
1.
Yeah, yeah, exactly. So we're going to need to do a little bit of math, but not a lot. And when mathematicians, came up with exponents, they decided that if you raise any number to the 0th power, it's going to equal 1. Frankly, because it made math easier. There's probably a principle behind it, but it also just makes a whole lot of math easier. I mean, there's definitely a principle behind it, but so what we're looking at over here is 100. Oops, excuse me. There we go. 100.
That should be 10.
That is 10. Thank you. Yep. I'll fix that in just a sec because this thing drives me nuts. If only like Zoom and TL could get married and have a baby or something. 100, 1,000. Right? Right? And in fact, what we're looking at here, what's linear here, speaking of linear and nonlinear, is powers of 10. Our x-axis is not a linear scale, it's an exponential scale, as in powers. And we usually see 2 raised to the first or the second because everything in computers is powers of 2 because of binary. The Find AI made this one with powers of 10. Who knows why? And so here, what we see is 2. I'll put these on the inside. 3, 4. And this just goes to show the weaknesses of AI because I'm not sure I quite understand their logic. I think the AI probably thought the scale would help with some sort of visual representation of the graph. But it doesn't. And in fact, I feel like this might just be plain old wrong as I'm looking at this. Because there's no way that this can be 10 operations when we have like 1,000 inputs. In fact, my trust in that graph has gone down significantly. So let me just pull up the one that we have floating around here, which is hiding in one of our curriculum lessons. And it's probably big O. In fact, it's this exact same diagram that we have floating around somewhere. And this is actually, I think, a really good resource. And so let's scroll down here and let's grab this. And there we go. Thank you for bearing with me there. And let's get rid of all this stuff. And this is a bit easier to see, I think, just because it's very visual and it doesn't have the weird scale. Um, and what we see here, all the way down here, this 0 sub 1, that's constant time. Here's linear time. So this is our simple search. I believe this is what's called binomial time. We'll talk about that in a second. Up here is exponential time. And we'll write a little bit of code as well. Though I actually think I always get this wrong. I think exponential time is over here. And when it's raised to the second, it's called quadratic time. Because exponential time, look at this. It's not 2 squared, 3 squared, 4 squared. It's 2 to the third, 2 to the fourth, 2 to the fifth. You know what I mean? So it gets huge really fast. Really, really fast.
Wait, just a quick clarification. Maybe I'm like overthinking it, but is the ones going straight up what you want? Like they're faster than the ones going to the right?
Other way around. Over
Okay,
here,
that's what I
we've
was.
got the number of operations it takes. So the
Mm.
higher up it goes, the more operations.
Okay, for some reason I was thinking operation time. Thanks.
Yeah, no worries. Yeah, and this is the thing. We say operations, but it means time. So the higher this is, the more time it takes. We don't talk about seconds. We just say like an operation, and that's some unit of time, some imaginary unit of time. And then finally factorial time, which is just huge. Though we will run into these as well, because sometimes it's the nature of the algorithm and the data that you're working with. And let's see if find can redeem itself. And let's just ask it to like give me a list of 2 raised to the 0 through the 10th power and its values. And let's just see how big this gets very quickly. So let's do expand on that. Let's tell find to expand on that through like 2 to the 20th and watch it just get massive. And we'll give find a moment to do its thing. And remember, this is our exponential graph. And look at how big these values get, right? It takes a while, 2 to the 4th over here going up through 16. Not really so bad, right? Not so bad. But look at where we are by the time we get to 2 to the 12th. Now we're way bigger, right? So here, our input size is n, right? As n is getting bigger, this is this exponential time. And normally when we see like exponential time and logarithms and stuff for data structures and algorithms, it's going to be powers of 2 unless it's said otherwise. And right here is when it starts to get massive, right? Because all of a second we go from 8,000, 16,000, 32,000, 65,000, 131,000, 262 here to a million. Right now, this is extremely big. And this, I think, is a really good example of why understanding the efficiency, the time complexity of an algorithm matters. Because if for some reason we have a search algorithm whose time complexity is 2 to the n, well, you know, good luck finding something, right? If we've got a lot of stuff. So these are kind of the basic categories of the different kinds of complexity that we'll see. And I just want to check in to see how people are feeling on this because this diagram here is really the main thing. And over the next several weeks, like we'll just be encountering these over and over again. Like big O of n times log n. I'll talk in a minute about what logarithm is. A log is essentially like log of 8 equals 3 because 2 to the 3rd equals 8. So a log isn't 2 raised to some power, but it's like what power do I need to raise to get that value? And just to go one smaller, log of 4 equals 2 because 2 to the 2nd power, 2 to the squared equals 4. Right? And log is not that bad. But exponential and then well, quadratic and exponential are where it gets really bad. And factorial we encountered before. This is, 5 factorial equals 5 times 4 times 3 times 2 times 1. And I'm sure you all can imagine after looking at how quickly the exponential graph grows, if we're doing 20 factorial, it's going to get massive. So let me just pause and check in and see if folks have any questions. And just to kind of recap, because I realize I've been jumping around a little bit here, let's circle back to really what we're covering. And we want to talk about simple search, this idea of runtime complexity and Big O. And also, do you all feel like you kind of get now why with Big O we only care about the worst case? Yes, no, maybe?
Yeah.
Cool. Yeah, because we've seen how big stuff can get, right? So hopefully we have a visceral understanding that Big O is worst case. And we've seen the really common Big O's. We'll see these all over the place, but just to relist them, Big O of 1, Big O of n, and this is in increasing order. Big O of I think log n actually grows slower than n. Don't quote, but don't quote. I want to double check that one. Actually, what ends up being really common is n times log n. Big O of n squared and big O of 2 raised to the n. And then finally, like the thing we want to avoid the most, big O of n factorial. Right? And this is sort of an increasing order of how long stuff takes, of badness, if you will. Though it's not really bad, sometimes you just can't get around it. And we'll talk more about Big O in the next lesson. I really kind of jumped ahead a bit. And we'll kind of like go through all of these. But I did want to introduce this because it's such a core concept. So why don't we can either push on or take a short break and write some code, because where I do want to take us now, we've covered simple search pretty well. Let's implement a binary search algorithm and talk about it. And I realize I'm running a bit long, and I ran over the hour, so I do apologize about that. Do you all want to, you want to take 10 and then we'll do binary search?
Sounds good.
Yeah, let's do it. Thank you very much, everyone. I'll see you all in 10 minutes, and then we will write some code that is going to be better than simple search. Thank you, and see you in 10. Okay. We'll put this off here for the moment. What we're going to talk about now is, it's way down here, binary search and divide and conquer. And there's a couple important things to know about binary search, and really like the two kinds of lists we can search through. There's really two kinds: unsorted lists and sorted lists. The phone book is a sorted list, right? The names are in alphabetical order. This list of numbers I've made over here, I'm going to make myself a little pointer. This is a sorted list, right? Each number of my list is in order. Doesn't have to be sequential. It could be 1, 3, 5, 7, 9, 13, 15, 17, so on. And actually in the future, I think that actually would be the cooler way to demo this, but it's sorted. It doesn't have to be sorted in increasing order, but it's sorted. And up here on the diagram, I've just made some indices. So different search algorithms work better for sorted or unsorted lists. Some only work for sorted lists. Binary search only works for sorted lists. And it's because it uses a strategy called divide and conquer. And in essence, divide and conquer, I think that's the right spot for that. Just those squigglies are going to kill my eyes and probably yours as well. Divide and conquer algorithms take a big thing and break it into a smaller thing. Keep breaking the smaller things into even smaller things until finally it's ridiculously small. Solve the ridiculously small thing, the small problem, right? We're going to break our list of 10 billion users into tiny and tinier chunks, and then combine the smaller bits together to get back to the bigger solution, aka divide, and then the combine is conquer. Let me give a concrete example of this. Just visually looking at this, and think here about the phone book, right? Or an encyclopedia, or even better, a dictionary. How many of you, like when you're looking up the definition of the word, I don't know, horse, have basically opened up a dictionary to the middle, seen what letter you were at, and if you were too far away from H, you went to the left, and if you weren't, you went to the right? Anyone ever done something kind of sort of like that, at least once in your life? And I appreciate people raising your hands. I know it's a rhetorical hand raising, but if the feedback helps me. And then you keep doing that. And that's the perfect example of divide and conquer. We divided until all we had to look at was a single page, and then it was really easy to search through and find it. Right? So if the number that I'm looking for here, if my target is 15, well, with simple search, I have to go all the way through. Right? My worst case performance is the length of the list. The algorithm, well, sorry. No, that's right. It's big O of n. Yeah, I'm just getting myself confused. Sorry. Ignore my confusion there. Binary search will let us do a little bit better. And again, instead of 16 things, think 1 billion users. Let's start in the middle. Let's divide. And eventually we're going to have like a couple different pointers, but we'll just call this one the middle one. And let's look at 8. And let's compare. Is 8 greater than 16? Nope. Is it less than 16? Yes. So I need to go here. And let's cut this in half again. And in fact, let me make another one of these so that we can keep track of our comparisons. And that was comparison number 1. And comparison number 2 is 12 to 16. And here, obviously, 12 is not 16. Once again, I know I don't want to go to the left. I want to go to the right. And let me make our screen real estate a bit bigger. Let's divide again. Let's do comparison number 3. $14, $16. Again, those are not the same. Let's do comparison number 4. And here 16 is 16 and we're done. Right? And I've sort of been, you could choose whether, if I wanted to compare to the left or the right of the dividing line, as long as I'm consistent, that's the important thing. And this is a good example here of divide and conquer, because once we have two things, this is trivial, right? And if we were looking for, oh, and in fact, the target is 15. I'm so sorry, folks. I hope someone saw that and just didn't tell me, because that does confuse things. So let me update that and let me look at the Zoom chat real quick. I see a question in Zoom. Can we search a dictionary without a loop? Yeah, the answer is no. Under the hood, Python turns a dictionary into a loop. This, if we're going to iterate through it, more or less. This is even better, because now let's do our last and final comparison. It gets a little messy here, but I don't even know if we need a comparison 5, to be honest, because by the time we get to this point, right? And let's maybe I can rotate this. One day I'll figure out how to rotate the things. By the time we get to this point, there's only one thing that we're looking at, and this becomes trivial, right? So this is a good example of divide and conquer. And this is the binary search algorithm in a nutshell. And this is what we're going to code up.
I have a question.
Yeah.
Why are you going to the end of the split instead of just the next one over the line so you only have to go one direction ever?
Say that again.
So right now you started we had 0 and 16 and you're looking for 15. You divide it in half. You say, okay, is it in this first half 0 to 8?
Mhm.
No, it's not. Instead of going to the end of the next half, why don't you go to the beginning of the next half? Because then at the very end, your last step, you landed at 16, you had to go to the left instead of to the right, which you've been doing the entire time, which induces some complexity that you're going to have to deal with. If you just go over the line by one and then search to the right every time, you'll never miss your target.
Yes. Does that work if we're searching for 2?
What do you mean?
Like if our target instead of 15 is 2?
Yeah, you would start at 0 and you'd split it in half. Oh, I see what you're saying. Um,
Yeah.
so yeah, it would if your target was 2. You'd split it in half. Is it less? Is it under 8? Yes. Okay.
Yeah,
Well,
you're
we've
basically saying, do I
you've
go
already
here?
you've already compared your search to 0. You know it's not, so you move your search over to 1 and then say, is it between 1 and 3? No, it's greater than that. Okay, now I can go to 5. Now I know, is it 5? Or I'm sorry, you would have moved to 2 and you would have found it on the second step
Um,
because you're assigning your search to compare to the thing you're currently on, right? And you're starting at 0.
yes. I mean,
Like, why does step 4 go to 16 instead of 15 first?
um, well, we can do it both ways. Let's actually do this with two and build this out. Or even better, let's do this with one. And because it's also possible I may have made a mistake here. Um, so let's start here where our target's one. Um, and so Tim, are you saying
I'm saying
basically
you should you should have
start
a
here?
point. Your pointer should start at the very beginning at your first indice to see if, hey, is it going to be this? And then if it's not, you split it in half and you say, okay, is it less than half? Yes. Well, we know it's not one because we already checked one. Move one more over, split it again. Is it between 2 and 4? Actually, it's 2, so we're done.
What if our target is, well, okay. So walk me through if our target is 6. What's the first comparison we should do?
All right. So you have a pointer that starts, you start at the very first item in your list here. Is it 1 in indice 0? No. What did you say our target's going to be?
6.
Okay. So we split it in half, 8 and
What do I
16.
split in half?
We split the here. Is
Okay.
it between where we're at now and 8, the half? Sorry, I forgot what we're looking for again.
We're looking for 6. No, I
Okay,
know. Because
so yes, it is. So split it in half again.
so split it like right. Let's see. One, two,
We
three.
so we already know it's not 1 because we've already checked it. So move to 2, split it in half again. Is it between 2 and 3? Or sorry, indices 1 and 3? No. Okay. Cool. Is it 5? No. Split it. Okay, cool.
Wait, if we split in half here,
Yeah.
sorry, that's huge. If if we're splitting in half here, how do I get from 1 to 2? What's the consistent?
Because every time you need a pointer to start to check a number. If you start with your pointer at 1, you say, is my answer here 1? Am I looking for 1? No, I'm not. Okay. Split in half here at 8. Is it fewer than 8? Yes. Okay, well, I know it's not 1, so I'm just going to move to 2 before I do my next check. I
Oh,
split it.
wait. So I think I figured. So you
Oh,
wouldn't know
hold
if
on.
it's fewer
Let's
than 8 without doing a search.
Hey guys, I appreciate it, but Tim, you're kind of in the middle of something, and I want to let you finish, and then, Jason, I'd love to hear what you were saying. Um, yeah, Tim, please.
Good. If you start it at the very beginning, you can eliminate this first variable and automatically move to 2 when you split. You split into 8. You split it in half with 8. You know it's somewhere between 2 and 8, right? You're looking for 6. Is it between you split it you split it again between 2 and 4? Is it there? No. Now you move to 5. Is it 5? No. Okay. Now you move to 6 before you split it again, and it was 6, so you stop.
I mean, I might have done part of it wrong, where maybe we should start out here, but if,
That way, I'm just saying if you do it consistently, you only have to go one direction ever. Instead of getting to 16 when you were looking for 15 and then saying, oh, no, I'm at the end of the list. I have to have a contingency for this. So I must have to go backwards now. You,
um,
I would think you would want to develop your algorithm to only travel one way for simplicity.
maybe we might end up doing that. It depends on how we implement the pointers, but the 1 to 2 step, I think, is, I'm not quite sure I understand. You're saying, all right, 1 is less than 6, so I cut my search space in half right here,
Mhm.
right?
All I'm saying is
And
if
then
you
I go
check it,
here and like 2 is less than 6, and I cut.
no, okay, so if you don't have to do that. If you're looking for 6 and you've cut it with 8, you know 1 is not your issue. So now you're only looking between 2 and 8.
Mhm,
So you split it in half.
mhm.
Is it greater than 4 or here?
Yeah.
If it is, you move to 5. You move no, you know it's greater than 4, so you move it to 5, which is the one greater than 4. So you've eliminated everything prior to 5. So stay on 5.
Okay, so we compared against 1, we compare against 4, and then
Yeah.
what's the next comparison?
Now you're looking between 5 and 8. You split it. You know, after I eliminate 4 because I know it's greater than 4, I would move the pointer to 5.
Yeah, but the way we're
I'm
going
sa-
to build this, it's going to be a little different because, like, here you started on the leftmost part of our slice. You know what I mean? It's like we kind of want the pointer to start at the same position with every slice. I honestly think if we build this, it'll help because I
so
may use
I
this a
never,
bit.
but I never pointed at 5. That's what I'm saying. I pointed at 1. I'm sorry, I never pointed at 4. I pointed at 1. I pointed at 5, and then next would be what, 6, and that would be the answer.
You might be right. Let's see, 1, 5. Yeah, you may be right here. I may have gotten this wrong. So this is our first slice in half. We look at 1. We know 1 is too small. We slice this space. Let's see, 1, 2, 3, 4, 5,
Your
6.
first slice is off by 1.
Thank you. That's There we go.
There you go. And then you move
Yeah,
to the right of the slice. That way you're only going one direction ever. You'll never have to go back.
yeah. Um,
But I mean, aren't we writing for like worst case scenario? Where we don't really know how when we know the numbers are sorted, but we still don't. But it's not always going to be like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, or whatever. It could be any arrangement as long as it's sorted. So
yeah,
when
I mean, that doesn't really affect it. I mean, you might be right, Tim. I might have walked through this wrong, but we're also going to build it in a sec. And when we see how the pointers are built, we'll kind of see what happens to here. Because here we start out here. The next one's to the right of the slice.
Hmm.
And if I follow that logic, my third one ends up here to the right of the slice at 7.
Well, it shouldn't because you did a comparison. Is it greater than 6? No.
Hmm. I don't actually do a comparison. I just do an equality.
Uh, okay.
Yeah, because we already know it's sorted. Um and 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 so in some ways I don't need to do the equality check. Let me code this up because I
Okay.
think Tim, you're right. I got a part of this wrong, but I also think when we see the code written, it will help us with the example. Otherwise, I think we'll just get lost in the sauce.
Okay. Sounds good.
Um, yeah, no, and I do appreciate you saying that because I think you're right that I added an extra step in there. So let's start building this out and then we can kind of see it in action. So it's going to take a list and we're going to pass it a target. Can everyone see this okay in VS Code, by the way? Okay, cool. Um, so there's a couple different ways to write this. We're going to use a while loop, so I need a sort of a counter. Well, and also I just want to count the number of steps. And now we're going to make some pointers. Because the way we actually need to implement this is a bit like this. And so what we end up with is, let me grab this guy here and just make it a whole lot smaller. Um, And we'll just make the low pointer orange, and we'll make the high pointer, oh, purple. So these pointers are going to do the mechanics of knowing what index to jump to slice. Actually, I think a better way is with the down arrow, so we can look at the index. Otherwise, I know that I will get confused. So I'll kind of build out the diagram as we go. Right, so we have a low and a high pointer. And what we do is we're going to move the pointers closer. If they are the same, we've met in the middle. So while the low pointer is less than or equal to the high pointer, right? Because eventually, at some point, what's going to happen is as these things get closer, if we somehow end up with both of them on the same thing, we know we've sliced through all the possible options and we're done. I'm just going to increment steps just for counting purposes. And I do need to have a middle pointer. And we're going to do, I think this is some floor division to take care of like if we have an odd number of things or really here with an even number of things, because the middle pointer can't point, right? If we just had 3 things, the middle could point just right here at 2, 1, 2, 3, and we actually have a middle value. But here we have to choose if we go with 8 or 9. And I'm pretty sure that floor division rounds us down. Let me just double check that real quick because I do always get a little lost on that. Like let's just do 3.5 or 2. Yeah, that rounds us down. Perfect. So let me make our middle pointer, and that one's going to be green, and it's going to point at index 7. And this was a really good discussion, by the way. And I did think I got a part of this wrong because this thing should end up being logarithmic time. But actually writing out the pointer logic I think is going to be the easiest way to see how this works. And we say we're going to look at the middle pointer and compare it to the target. And if it is, then we're done. And we're just going to return the index and the number of steps. But if it's not the target, and then we have to handle it a bit differently. If we are low, and Tim, you're right, we are doing this here. And what did I miss in my... Oh, I don't want the column there. That's what I don't want. Because now we have to decide, do we slice left or right next? Right? Wherever we put the pointer, Tim, you're right. Like if I slice here, I need to do a comparison to decide if my next slice is here or if my next slice is here. And we need to increase the low pointer, and we'll walk through what this is doing in a moment. And let's have it return -1 and the number of steps. And let me get a little more screen real estate here. And what we can do is we can just run this with this exact scenario. Let's just make a list. I'm just going to type it out because it's easy and fast. And now let's print the output of a binary search on my list for the target. We might as well just stick with 6. And we're going to want a little bit of screen real estate. Unfortunately, we probably don't have time to use the debugger, which would be really cool, but we can be a manual debugger with our pointers and TL draw. But that's another great way to walk through exactly what's doing, is to hit some breakpoints and run the debugger. And let's see here. This just looks like on line 4.
Your -1
The
needs to be
-1 needs to
outside
be
the
outside.
parentheses.
Oh, yeah. Thank you. Yeah. To be honest, I don't really like assigning variables this way. I think it's a bit of an anti-pattern for exactly this reason. It's like you save one line, but it decreases readability. And length list -1. And it's not LIST, it is LST. And I need to make that change here as well. To be honest, I think the variable name LST is a little dangerous in that regard. If I'm like one letter off from spelling a normal word, that would cause a problem. I try to avoid that variable name. So we got an answer, but let's add some print statements in here so we can also see what's going on. So first off, let's just add an F string and just say step. We'll put it right there. And let's say mid, and just print that out. And let's also print out our low and high values. And then we'll get everything printed out nicely over here. Instead of printing this out, let's actually just grab this. And we'll just call this IDX total steps. My list sub X. At index IDX. And let's run this and see if there's anything we need to debug here if we're good to go. Okay, awesome. So let's walk through this now that we've run it and see if the code is right and see how this algorithm is behaving. So at the first step, our low's over here at index 0, high is at index 15, our mid is at index 7, right? So we have to choose one or the other, and we chose floor division. So we do a comparison right here. We're saying, hey, does the value of the mid equal the target? Well, nope, it doesn't. The value of 8 does not equal our target of 6. So we move on to here. Is the value of the mid less than the target? Well, no, it's not. 8 is greater than 6. So we go here. We need to shrink our search space. And we bring the high over here to the mid pointer -1. And then we get into the next step, step 1, where our low pointer is still 0, our high pointer is at 6, and the mid pointer is now at 3 in the middle. And again, as I said, Tim, I think you may have been right here about a piece that I missed. And let me add like a star just to kind of track each thing that we've compared. And so that's our first, and by comparison, I mean this if statement right here. So that's our first comparison. Now we're going to do our second comparison, and we're going to say, hey, does the value at the mid pointer equal our target? Well, the value here at 3 does not, the value is 4 at index 3. Sorry, it's confusing. Well, in fact, let's have them just look like this. They're not the same. Well, is that value of 4 less than the target? This time it actually is. And let me go ahead and mark that we've done a comparison here. Yeah, and folks, I apologize. I did get the diagram wrong, I think, the first time, which is why honestly writing the code helps, because it is easy to get lost in the sauce with pointers. So the value we're checking of 4 is indeed less than our target of 6. So we swing up the low pointer here and we put it right there. And then we come to our next part of the loop where our mid pointer gets set right here. The high one we don't touch. And we do our comparison, and indeed we find the target on step 2. And Tim, I think this is kind of the direction you were going in. Is that right?
That's exactly what I was trying to explain, but I guess I wasn't conveying it very well.
Yeah. Well, to be honest, you may have been. It's also Friday afternoon. And so I apologize if I misunderstood, because I clearly had an extra step there and was getting something wrong. And sometimes I just need to lay it out. But this way we ended up laying out really nice, and we walk through it and we can see what's going on. And also with these 2 pointers, we can see what's happening. And we end up only having to do 3 comparisons to get here, which also happens to be log of 8 because 2 to the 3rd equals 8. So this binary search is actually big O of log n, which is way more efficient, right, than constant time. Yeah, and again, I apologize for getting lost in the sauce drawing those diagrams before. I'm glad we ended up sorting it out, and thank you for your guys' help on that. So this is why
faster than
logs
Ovaltine.
are so nice, right? Because this is way more efficient. but we can only use it on a sorted list. And that's binary search. And this is probably a good time to check in and see what questions folks have and things that people are curious about.
I just had a quick note. I was curious to an actual number of how much time this would save. So I just asked Claude AI, and it was if you had a list of 1 to 10 million and you searched sequentially, it would take 10 seconds to find the average number. And then if you did the binary, it would take 0.00025 seconds. So I guess working with a lot of numbers, it makes a lot of sense how much time it saves.
Yeah. A list of let's see, what's a really big power of 2056. That's log base 2 of 2056. Google is so good at this. In fact, we'll just give it to you. So now the A. Oh my God, this is not. I just no.
Wait, I may have a website that can help you out. May I share?
One moment. Let's see if we can just get the answer here. 3.13. So basically, no, let's see. See, 2 to the 8th. Okay, here we go. My brain is definitely tired. And it's 2048. That's the problem. Okay, perfect. Because what I wanted to show is, and this is why the powers of 2 are nice, because everything in the computer is powers of 2. 2 to the 11th equals 2048. Right? So with simple search, list length n is 2048. Simple search, big O, n 2048 steps. And as to your point, Chase, let's just pretend we have the world's slowest computer and every step takes a second, and that's 2048 seconds or whatever. And then with binary search, we're looking at, as its big O of log n, which in this case is log 2048, which is 11. So we're looking at 11 steps. And what were the numbers that you looked up again, Chase, for that sort of real world point of comparison?
It was 10 million basically, and 14 steps or 24 steps.
And how many seconds or milliseconds was the difference?
24 microseconds, but the difference was 10 seconds in total.
Yeah. Yeah, no, the difference is huge. I mean, and you all can see that here. We have to do 2048 steps in our worst case scenario. With binary search, it's just 11. And Kenny, I think you're going to say something as well.
Oh, I have something that can visually explain this, if you don't mind me sharing.
If you can you drop it in the chat? And I think because I know we've ran a bit long, so I do want to wrap up the lesson, but then I can absolutely screen share it and we can look at it and discuss for a little bit.
No problem. It's just a graphing app, a graphing website that just shows all of this.
Oh, okay. Yeah, what is it?
Oh, let me just share real quick. I already got the inputs in there.
Okay, go for it.
So this is Desmos, something that we use in college and also high school.
Oh,
So
this is
if
awesome.
X
Yeah.
is the inputs, P is the amount of, I believe, steps it takes. So here you can see that constant time for 10 steps, it takes 10 operations. And here's the equations. O is the inputs, and P is how many steps it takes. And what you were just mentioning, the log for
Yeah.
Even 200, even for 150 steps, it doesn't even get to one. It barely gets to two.
Yeah. No, this is awesome. Thank you so much for sharing this. Yeah, please do drop the link to that in the chat actually, because I definitely want to use that like moving forward, and I think that's a good one for people to see. Um, yeah, that was awesome. Thank you again. What other questions do folks have about the binary search algorithm before we wrap up?
I
I'm
mean, I think
confused with
I'm.
names. Go ahead, Jack.
Oh, I was just gonna say, I get the bigger picture, but are we like really gonna be needing to figure out what our log of O is for anything, or is it just for like understanding purposes?
It's just for understanding purposes. Like really the main thing, really you just want to be able to recognize linear, quadratic, log of n, and then it's like exponential and factorial. So we're not going to actually have to calculate numbers. You just kind of want to be able to sort of be able to visualize a bit the curve. Um, though it is helpful to get comfortable with powers of two because they're just everywhere. And there's a reason that the binary search is logarithmic, and it's because we're dividing by two our search space every single time. But no, we're not going to have to like do any sort of number crunching or anything like that. Yeah, good question. What else is on people's minds?
Other than since you can only use these on sorted list, how would you use it on data unless the answer is just convert it to the actual CHR code
Yeah, that's a great question.
or the
So,
ASCII code, sorry.
um, well, yeah, with letters, we don't have to worry. It's exactly what you said with letters. Like if I have a list that's like this, you know, we'll just use, as you pointed out, like under the hood, Python is already representing each of these as a number, and indeed, like it's in an increasing order. So, I mean, in fact, it could even be with words as well, because literally each letter you can think of it as just having an integer value, right? And so it's really easy for Python, and because you pointed out it has to represent letters as numbers with ASCII codes anyway, to just have a number value for these things so it can do comparing. Um, if we had a list of lists, then we might have to write our own comparison function that we would use here. Maybe I can't just straight up do this and this. Maybe I have to say, if my comparison or something like that, if that makes sense, which we kind of saw a bit with higher order functions and stuff. But you all could imagine writing a function that adds these two numbers together to get a value and using that and kind of dropping it in here and here to do the same job, right? Same with dictionaries if we really needed to, right? So we might have to write our own logic to do the comparison, the equality and comparison operations. But as long as our data is sorted, that's very well within the realm of the doable. And just to kind of add to your point, if we're building an address book, maybe when we're writing the code, the way we design the program is when I add a new user to the list of all the users, I sort it right then. Because we'll learn this later, but it turns out if I've got a list that's sorted and I want to add something to it, and keep it sorted, that's easy, right? If I've got, in fact, we might even be able to use like a divide and conquer binary search approach to do that, to add to a sorted list, though don't quote me on that. Let me just make our box a little bigger just so I can have an intermediate number. Right. The same way divide and conquer works here. Like if I want to put 4.5 in the right spot, I actually can do something pretty similar where we check here, we go here, and then we drop it in. If this list is totally unsorted, then I have to go through every single thing. So when we're designing programs, like if we have lists of stuff and we need to care about the efficiency of searching it, sorting as we go is way more efficient and cheaper and easier. But again, if I only have 100 users in my program that I'm writing for tomorrow's homework assignment, and the goal isn't data structures, then honestly, the answer is who cares, right? Like we don't need to introduce that much complexity unless there's a good reason for it. Yeah, great question. And then obviously if the list is unsorted, we're just sunk and we can't use binary search for it. But it just goes to show there's lots of ways we can get to having a sorted list. What other questions do folks have? What else is on people's minds? Okay.
Because, sorry, I had one
Oh
more.
yeah, yeah.
Because sorting algorithms are usually pretty resource intensive, right? It takes a lot to sort any kind of complexity into something meaningful.
Mhm.
Is it typically a better idea to sort something and then use binary search as opposed to just using search methods designed for unsorted
Yeah, that's a good
data?
question. And by resource intensive, do you mean like they take more steps
Yeah,
algorithmically?
yeah. Your O of N is going to be a lot higher.
Yeah. Yeah, exactly. You were saying, is it more efficient to sort something and then use binary search for some other search algorithm?
Yeah. Is it better to because there are obviously algorithms designed for
Mhm.
unsorted data. Is it better to use one of those from a resource standpoint or just a calculating your O or sort it and then use
Yeah.
binary search?
If you can, right. If you can sort as you go, as you build it, that's almost always going to be cheaper. Because I don't think there's a way to get a logarithmic time search algorithm on an unsorted list, right? Because this really nice log of n curve that we get, it's because we get to slice stuff in half and leverage the power of two. And we can only do that if the list is ordered. So I hate to say in general, because the truth is it always depends on specifics. But in general, yeah, if you have to care about search efficiency and you can sort as you go, there's probably a good plus to that.
But if you inherit a giant data set that's unsorted, is it worth the time to sort it in order to use binary search in the future?
It
Or
would
is it,
depend. Oh, sorry, I didn't mean to cut you off.
no, that's fine. That was
Yeah,
essentially my,
that's a really good question, right? If I have an unsorted list, do I want to sort it and then use binary search? And the answer is it depends on how efficient the other search algorithm is, right? I think like let's see, like I don't remember a search uh, classic search algorithm efficiency. Let's just find one real quick and we can just see. Um, yeah, I just want a list of, yeah, big O of N. I get, big O of N is probably the next best up. There might be something faster. Um, I think the short answer is it depends. Um, you very well may be right. It might make sense to sort it first and then search. You also have the advantage of once it's sorted, it's easier to keep it sorted. Though it depends what you're doing. If we're doing some sort of batch data processing, then it's a different story. What are some simple search algos and their efficiencies? My brain is just tired and it's the end of the day and I can't remember this, but I think this will help answer our question. Now, binary search doesn't work for us because it only is sorted. This next one is also sorted. Only show me ones for unsorted lists. Oh man, what? Yeah, short answer is going to be it depends, and actually, here's the better takeaway. That is a great question for a technical interview, right? And really, the task is not necessarily to get the right answer, but to be able to see the different options and discuss their trade-offs. So that if I can go into an interview and talk about, should I be sorting my data and then applying binary search or use some sort of other search algorithm for an unsorted list, that is a good discussion to have. This is a cheat because this is building a dictionary out of a list. So we get incredibly good time complexity, and it does really the same thing like you were saying. I'm honestly, I apologize because it's the end of the day and I'm blanking trying to come up with like some other search algorithms for unsorted lists. Because basically, I think you're right, Tim, because this is reminding me, and as we look at this, like it's so much easier to search a sorted list. And so like so many of these strategies, depending on having some sort of sorted list. Yeah, so that was a long answer to a short question. But yeah, the answer is if you can, you probably want to sort and then search.
Okay, thanks.
Totally. It's not uncommon to create a dictionary and a list. And as you put stuff in, build up the dictionary as well as the list. Because when we're adding new data to our phone book, it's cheap and easy to do that, right? And we trade time for space. The dictionary takes up more space, but then we get to look stuff up instantly with the constant time search. So it again, it depends on what we're trying to do and what we want a program to do. But yeah, that was a great question. All right, on that note, why don't we wrap up? Because I realized this ran a bit long. So thank you, I appreciate it. I hope it was useful. The lesson video will go up in a little bit. We do have assignments for this, and I do recommend doing them. Even if they might feel like review, that just means they shouldn't take you very long. So just go ahead and knock these out. And they're good ones because we throw in a couple of things in the mix and you can implement linear search and binary search, and that'll help build your mental model. If nothing else, use the debugger and step through binary search or do what I did with TL draw and the pointers or a piece of paper. Like this was a lot of my schoolwork as an undergrad doing this on paper, over and over and over and over. And then as a stretch assignment, basically go back and look over some of the week 1 programming problems, right? They're a little more algorithmy, and start thinking about if you can make it more efficient. Can I create a dictionary and put stuff in it as I go to give myself a really nice constant time lookup later on? So I think this one is definitely worth doing, and really the second one as well, because you'll look at the week 1 problems with fresh eyes. And then next Friday, we'll continue on. We've covered a good amount of the ground because we talked a whole lot about Big O today. But tomorrow, we will do a more proper walkthrough of logarithms and Big O. All right, folks.